The National Electrical Code allows for a smaller wire size for the neutral conductor in certain scenarios. However, it is important to ensure that the neutral wire has sufficient capacity to carry potential unbalanced loads. For underground service entrances with conductors larger than 200 feet, it is generally recommended to use the same wire size for both the hot and neutral conductors. This ensures that the neutral has sufficient capacity to handle any potential unbalanced loads. The NEC does permit a smaller wire size for the neutral under specific conditions, known as neutral resizing. These exceptions include firstly, 3-phase, 4-wire systems. The neutral wire can be sized smaller than the phase conductors if the neutral current is limited by specific design considerations. Secondly, single-phase systems with balanced loads. In certain cases, if the load on the hot conductors is known to be balanced, a smaller wire size for the neutral may be acceptable. However, this should be carefully evaluated and documented. For a 240-volt service entrance with size 250 volt conductors and a distance of over 200 feet, it is safest and most compliant with the NEC to use size 250 for the neutral conductor as well. This eliminates any potential concerns about unbalanced loads or future changes in the electrical system. Always consult the latest edition of the NEC and local building codes for specific requirements and guidance. Let's delve into the technical considerations for selecting the appropriate neutral wire size for an underground service entrance, particularly when dealing with distances exceeding 200 feet and a specified size of 250 for the hot conductors. The primary concern revolves around ensuring the neutral conductor's capacity to handle potential unbalanced loads while adhering to the National Electrical Code requirements and maintaining electrical safety. When sizing conductors, voltage drop is a critical factor, especially over longer distances. The NEC recommends limiting voltage drop to no more than 3% from the service point to the furthest outlet. In this scenario, with the distance exceeding 200 feet, voltage drop calculations become even more crucial. Using a conductor size of 250 for both the hot and neutral conductors mitigates voltage drop concerns, ensuring that the voltage of the panel remains within acceptable limits, even under load. The NEC addresses neutral sizing in various sections, allowing for a reduced neutral size under specific conditions. These conditions typically involve scenarios where the neutral current is expected to be significantly lower than the phase currents, such as in balanced 3-phase systems or when dealing with predominantly linear loads. However, when dealing with single-phase systems or systems with the potential for unbalanced loads, such as residential services, it is generally recommended to maintain the same size for the neutral conductor as the hot conductors. This recommendation stems from the potential for unbalanced loads to cause significant current flow in the neutral conductor. Unbalanced loads occur when the current draw on each phase of the electrical system is unequal. In a 240-volt single-phase system, this can happen when appliances or loads are connected unevenly across the two hot legs. For example, if one hot leg is heavily loaded while the other is lightly loaded, the neutral conductor will carry the difference in current between the two legs. If the neutral conductor is undersized, it can overheat, leading to insulation damage and potentially creating a fire hazard. Furthermore, an undersized neutral conductor can contribute to voltage imbalances in the electrical system, affecting the performance and lifespan of connected equipment. In cases where the load is known to be balanced and is expected to remain balanced, a reduced neutral size may be permissible under the NEC. However, this requires careful analysis and documentation to ensure that the neutral conductor has sufficient capacity to handle any potential unbalanced conditions. Moreover, future changes to the electrical system may introduce unbalanced loads, rendering the reduced neutral size inadequate. Therefore, unless there is a compelling reason to reduce the neutral size, it is generally advisable to maintain the same size for both the hot and neutral conductors. Using size 250 for both the hot and neutral conductors provides a safety margin, ensuring that the neutral conductor has sufficient capacity to handle any potential unbalanced loads without overheating or causing voltage imbalances. Additionally, this approach simplifies the installation process and eliminates the need for complex calculations and analysis to determine the appropriate neutral size. It is also worth noting that some jurisdictions may have local amendments to the NEC that further restrict or prohibit the reduction of neutral conductor size. Therefore, it is essential to consult with local building codes and electrical inspectors to ensure compliance with all applicable regulations. In addition to conductor size, other factors to consider when installing an underground service entrance include conductor insulation type, burial depth, and protection from physical damage. The NEC specifies minimum burial depths for underground conductors based on voltage level and installation type. Proper burial depth protects the conductors from damage caused by digging or other activities. Furthermore, conductors should be protected from physical damage by encasing them in conduit or other approved raceways. Schedule 40 polyvinyl chloride conduit is a common choice for underground service entrances due to its durability and resistance to corrosion. When installing conductors and conduit, it is important to follow the NEC guidelines for conduit fill. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. Overfilling a conduit can make it difficult to pull conductors and can also lead to overheating due to reduced ventilation. The NEC specifies maximum conduit fill percentages based on the number and size of conductors. In summary, when running an underground service entrance with size 250 hot conductors over a distance of 200 feet, it is generally recommended to use size 250 for the neutral conductor as well. This approach provides a safety margin, ensures compliance with the NEC, and simplifies the installation process. While the NEC does allow for reduced neutral sizes under certain conditions, these conditions require careful analysis and documentation and may not be suitable for all applications. Always consult with local building codes and electrical inspectors to ensure compliance with all applicable regulations and to address any specific concerns or requirements. The selection of the appropriate neutral wire size for an underground service entrance is a critical aspect of electrical system design and installation. The decision should be based on a thorough understanding of the National Electrical Code, potential load imbalances, and local building codes. While the NEC permits the use of a smaller neutral conductor under specific conditions, it is often prudent to use the same size conductor for both the hot and neutral wires, especially when dealing with long runs and potential for unbalanced loads. Firstly, the NEC guidelines for neutral conductor sizing are outlined in Article 220.61, which addresses the reduction of neutral conductor size. This section allows for a reduction in neutral size based on the type of load served and the harmonic content present in the system. However, these reductions are subject to certain limitations and conditions. Secondly, the potential for unbalanced load significantly influences the neutral current. In a balanced three-phase system, the neutral current is theoretically zero, as the currents from each phase cancel each other out. However, in single-phase systems or three-phase systems with unbalanced loads, the neutral conductor carries the difference in current between the phases. This unbalanced current can be substantial, especially in residential or commercial settings where loads are not evenly distributed. Thirdly, the length of the service entrance conductors impacts voltage drop, which is a critical factor in conductor sizing. Longer runs of conductors result in increased voltage drop, which can negatively affect the performance of connected equipment. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and feeders. Therefore, when dealing with an underground service entrance exceeding 200 feet, voltage drop calculations should be performed to ensure that the selected conductor size is adequate to maintain voltage within acceptable limits. Fourthly, the type of load served by the service entrance is another important consideration. Nonlinear loads, such as electronic devices and fluorescent lighting, generate harmonic currents that can significantly increase the neutral current. Harmonic currents are multiples of the fundamental frequency of the power system and can cause overheating and other problems in the neutral conductor if it is not adequately sized. Fifthly, local building codes may impose additional requirements or restrictions on neutral conductor sizing. Some jurisdictions may have stricter interpretations of the NEC or may require the use of larger neutral conductors than specified in the NEC. Therefore, it is essential to consult with local electrical inspectors and building officials to ensure compliance with all applicable regulations. Sixthly, the use of a reduced neutral conductor size should be carefully documented and justified. Electrical engineers and contractors should maintain records of all calculations and assumptions used in determining the appropriate neutral size. This documentation is essential for demonstrating compliance with the NEC and for troubleshooting any problems that may arise in the future. Seventhly, the potential for future load growth should be considered when sizing the neutral conductor. Electrical systems should be designed to accommodate future increases in load without requiring major modifications or upgrades. Therefore, it may be prudent to use a larger neutral conductor than currently required to provide for future expansion. Eighthly, the cost of using a larger neutral conductor should be weighed against the potential benefits. While using a smaller neutral conductor may result in some cost savings, the potential risks associated with an undersized neutral, such as overheating and voltage drop, may outweigh the cost savings. In many cases, the additional cost of using a larger neutral conductor is relatively small compared to the overall cost of the electrical system. Ninthly, the experience and judgment of qualified electrical professionals should be relied upon when making decisions about neutral conductor sizing. Electrical engineers and contractors have the knowledge and expertise to assess the specific conditions of each installation and to make informed decisions about conductor sizing. It is always advisable to seek the advice of a qualified professional when dealing with complex or critical electrical systems. Tenthly, consider the practical implications of using different conductor sizes for the hot and neutral conductors. Using the same size conductor for both the hot and neutral wires simplifies the installation process and reduces the potential for errors. It also ensures that the neutral conductor has adequate capacity to handle any potential unbalanced loads without overheating or causing voltage drop. In conclusion, the decision of whether to use a smaller neutral conductor size for an underground service entrance should be based on a comprehensive analysis of the National Electrical Code, potential load imbalances, local building codes, and the specific conditions of the installation. While the NEC permits the use of a smaller neutral conductor under certain conditions, it is often prudent to use the same size conductor for both the hot and neutral wires to ensure electrical safety and reliability.